Hi, I'm Nishka, and welcome to Probability Magic, a module presented by Carnegie Mellon University's Leonard Gelfand Center. Hello, and welcome to Probability Magic. We always say that math and science surrounds us through every minute of every day, and the same can be said for probability, which is a concept that can be simply explained as what are the odds or what are the chances of something happening. And we think about it on a daily basis. For example, if you're playing basketball, and you're standing at a line and thinking, what are the chances that I can score a three-pointer from here? Versus what are the chances that I'll make it in the basket if I pass it to my friend first? These small decisions affect our lives every day. Additionally, if you've ever had to make lunch for your family, you know that the chances of someone eating 2 or 3 sandwiches is a lot higher than someone eating 50 sandwiches for that one meal. And these kinds of decisions aren't just limited to the home. Many professionals use probability on a daily basis to do their jobs and make important decisions. Some examples of people who use this every day include sports statisticians, people who predict weather patterns, election results, and more. So while you can use probability in this module to help improve your decision-making skills and get better at winning card games, you can also think of it as a skill necessary for life. Hello, and welcome to the Probability Magic module. Let's get started. Here are the materials you're going to need to complete this module. 2 sheets of lined paper and a pencil, the M&M probability handouts, 1 die, or you can use to create a die handout to make your own, 1.69 ounce package of M&Ms or Skittles, 1 plate, and 1 calculator.
Instead of candy, you can also use a different small multicolored object, like colored paper or colored paper clips.
Let's get started with some probability. Now it's time to fly on over to part 1. In this part of the module, you'll be understanding some key terms to familiarize yourself with probability and play a fun game to test your knowledge. Since this is a probability module, I will first explain the concept of probability, or the likelihood that an event will happen. But for many of us, the term likelihood may also seem new. We can think of likelihood as the chance of something happening. For example, we can think, what are the chances of seeing a penguin in a warm country in the middle of summer? Most of us would say that this is a very unlikely event. Or we can use it to estimate things that we do not yet know. Let's say you have a big jar in front of you filled with different colored marbles. We can describe our chances of picking out a blue marble from this jar in terms of likelihood as well. In order to find the probability of picking out a blue marble, we can use a simple probability formula. But before we look at that formula, let's take a closer look at likelihood and answer this question, what are the odds? Likelihoods can be certain if there's a 100% chance of the event happening, or impossible if there's a 0% chance of the event happening. But we also have different likelihoods in the middle, unlikely, equally likely, and likely, that we'll take a closer look at later. So let's take a look at a jar and then some marbles. If I have a jar with me and an assortment of different colored marbles, what would be the likelihood of picking out a certain color marble? But in this case, I'm going to start with 6 pink marbles. And one by one, I'm going to drop these marbles into the jar. And now we've got all of our marbles in the jar. So the question is, which color marble will I select from the jar? And now when I take out all the marbles from the jar, we can see that we have all 6 pink marbles. And so the likelihood of picking out one of these pink marbles would be certain because we only had one color going in there in the beginning. So there's a 100% chance of picking out a pink marble. However, this answer would change if we changed up some of the colors of the marbles that we have. So let's make 3 of these marbles blue. And now I'm going to drop these marbles into the jar again. Now it may not be as clear which marbles I'm going to select from the jar at first. So here are the pink marbles that we're pulling out of the jar, and now the blue ones. And as we can see, 3 of the marbles are pink and another 3 of the marbles are blue, so the likelihood of picking out a pink marble is not certain anymore. Since they are split equally, it is now equally likely that you will pick out either a pink or a blue marble. And as we can see from this chart, equally likely lands right in the middle where you have half of your marbles of one color and half of your marbles of another color. So the odds of picking out a pink marble and a blue marble are equally likely. Let's try this again one more time with all blue marbles. So I'm going to drag all the blue marbles into the jar just like I did last time. So think to yourself once again, what is the likelihood of picking out a pink marble from the jar? Now you might already know the answer to this, but let's make sure you're right. Did I hear you say that you thought the likelihood of picking out a pink marble from the jar would be almost 0? Well, if you did, you'd be correct, because as we can see, we have only blue marbles in this jar. So after counting the colors of the marbles of the jar, we now know that the odds of picking out a pink marble are impossible because there are 0 pink marbles in this jar. And that's all there is to know about likelihood. Get ready to play a fun game to test your knowledge. Hi again! Get ready to play the shell game. This game starts with the marble and some cups. At the start of each round of the game, I'll be putting the marble under one of the cups. Then I'll move them around all over the table. When I'm done, it's your turn to select the cup that you think the marble is under. It can get tricky, so make sure you keep your focus on the cup with the marble throughout the whole game. And how does this game tie back to the term likelihood that we just learned in the previous part of the module? As we increase the number of cups, do you think it'll get harder or easier for you to pick the correct cup? It may actually get harder for you because if we were to understand the odds of randomly picking out a marble from underneath the cup, they would get lower each time a cup is added. If we only have 2 cups, the marble can either be under the first one or under the second one. Not too bad, right? Now let's take a look at what would happen if we added another cup. Now let's look under cup 1, cup 2, and cup 3. Okay, so this time it was a little bit harder. So let's take a look at how this relates to likelihood. The odds of picking out the cup with the marble underneath it are pretty unlikely because we have 3 total cups and the marble can only be found under one of them, so our likelihood is roughly around 33% or 1/3, which falls between unlikely and equally likely. However, in the previous example, we only had 2 cups and the marble could be found under one of them, so there was a 50% chance you would guess correctly, or an equally likely likelihood. Now on to part 2. This next part will involve M&M probability. This will help you answer the question, what are the odds of finding a blue M&M in your bag? And create fun candy graphs. Math is sweet. Are you ready for M&M probability? For this module, here are the materials you're going to need. Your M&M probability handouts, a calculator, a pencil, 1.69 ounce bag of M&Ms, or just one of the standard size bags. And if this is hard to find, you can always use 2 small individual bags of M&Ms instead. Note that you can also use Skittles, but this might change how you make your graph and fill out the M&M probability handout. Lastly, you will need 1 plate. Also, make sure to ask your parents if you're allowed to eat the M&Ms, and make sure to wash your hands before starting, just to keep everything clean. Feel free to pause the video now to collect your materials. In order to get started, get your plate and your package of M&Ms and pour the M&Ms onto the plate, and then start sorting them by color. Now count how many M&Ms you have of each color and write this down on the top of your M&M probability handout. If you have more than 13 of any one color M&M, feel free to put the extras to the side. You won't be needing them. Now we can count how many M&Ms we have of each color and record them on our M&M probability handout. Once we're all done with this, we're going to add up all the colors and write down the total number of M&Ms that we had in our bag. You can use a space under the word total as scratch paper to help you with your addition. Great! Now that we have our total, let's move on to the next part. If you still need more time, feel free to pause the video. Now we're going to start working with some fractions and probability. So take the number that you got as your total and write it down on each of the lines underneath the chart that you see in the middle. So the probability of selecting a blue M&M equals, then I'm going to put the total on that line and repeat that for every other color. I'm also putting a little bar on top of the numbers to signal that this total is going in the denominator of the fraction. Once you have the total number of M&Ms written down on each line, you're going to write down the number of M&Ms of one specific color. So, in this case, for your probability of selecting a blue M&M, look at the total number of blue M&Ms that you got on top, and add them to the numerator of the fraction. Do the same thing for the rest of the colors, starting with red, then green, yellow, brown, and orange. But you might be wondering, what does this probability formula actually mean? So we've looked at the total number of M&Ms we have in our bag and the number of M&Ms of one color. When we put them into the fraction, here's what it's telling us. For example, on my sheet, for the probability of selecting a blue M&M, we've got 13 out of 59 total M&Ms. And it's hard to imagine what this exactly means unless we look at it on that likelihood scale. In order to make that step easier for us, we're going to convert our fractions into percentages. In order to do this, divide the numerator, or the top number, by the denominator on any calculator that you have. In my example, I had 13 blue M&Ms. I'm going to divide the number 13 by the total number of M&Ms I had, which was 59. So 13 divided by 59. And I get this output on my calculator. This is a decimal, and in order to convert it to a percentage, which is what we want to look at, just move the decimal point 2 steps to the right. So this 0.22 turns into approximately 22%. And I'm now going to repeat this process with the rest of the colors. If you want to calculate these percentages on your own, feel free to pause the video now. If not, continue to follow along. Let's look at these percentages we calculated on the likelihood scale. 22% falls right before unlikely, so it's between impossible and unlikely. 20% also falls in this range. 7% seems a little less likely, closer to the left of this chart. And then 22% is the same as the blue M&Ms that we saw earlier. Looks like the yellow M&Ms are a little less likely as well. And the orange M&Ms come up at 17%. Maybe the likelihoods and percentages were a little bit confusing, but don't worry, that's where the bar graph comes to help us. What we're going to do now is take the second page of your M&M probability handout and lay it out flat on a table in front of you. Then get all of your M&Ms and start placing them in the right color columns going up. Repeat this for all of your M&Ms. This bar graph should make it a lot easier to see how many M&Ms you have of each color. As we can see from my chart, the most M&Ms I have of each color include red, green, blue, and then orange, which comes close. I have the least amount of brown or yellow M&Ms. So when I reach my hand blindly into the bag and pull one out, it seems like the likelihood of picking out a red, green, blue, or orange M&M is higher than picking out the brown or yellow. Time for part 3 of the module. Now's your chance to think like a scientist and design your very own experiment. All you'll need is a die and some paper. Life is filled with random events. But what do we mean by the word event? An event is one or more outcomes. For example, we can have an event with one outcome, which would be rolling a 1 on a die, or an event with multiple outcomes, rolling an even number on a die. And what do we mean by this? Let's take a look at this die. If we want to roll a 1, there's only one way to do it, to land on the 1. But if we want to roll an even number, there are 3 ways to do it, either landing on the 2, the 4, or the 6. So this is the difference between an event with one outcome and an event with multiple outcomes. There are 2 types of events. There are independent events, or an event that is not affected by another event, and dependent events, or an event that is affected by other events. Let's look at an example of an independent event. First, let's simulate rolling a die. You roll a die and got a 4 on your first roll. Now, we roll it again. And this time, when you roll it again, you get a 3. These rolls are independent events because rolling a 3 was not affected by the previous roll where you got a 4. Now here's an example of dependent events. Let's say you draw a card from a deck of 52 cards. Looks like you got a 3 of hearts. But now you want to draw another card without putting the 3 of hearts back in the deck. It turns out that your chances of selecting a 3 from the deck are now smaller. And this goes back to the probability formula that we learned in M&M probability. This formula was the number of favorable outcomes you could get over the number of total outcomes. The total number of outcomes is now 51 instead of 52 because we originally had a full deck but removed one card, the 3 of hearts. And the number of favorable outcomes is now 3 instead of 4 because we removed the 3 of hearts earlier and never put it back. This is an example of a dependent event because the probability of picking out a 3 from the deck went from 4 out of 52 to 3 out of 51. And the event of picking out a 3 for the second time was affected by picking out the 3 for the first time. Now you can start designing your very own experiment. The 3 steps of an experiment include 1. Constructing a hypothesis. In this example, we will be rolling a die over and over again. Do you believe the die will land on an even number, less than half of the time, exactly half of the time, or more than half of the time? At this point, if you want to think about your answer, pause the video, and then replay when you're ready. In step 2, we will be experimenting and performing trials. And in step 3, recording our results to answer our initial hypothesis. It's time to get experimenting. Roll the die and write down the number you get. Now, roll it again and write down the number. We're going to be repeating this step 50 times. In order to keep track of each time you roll it, I would recommend writing down 5 numbers at a time and then moving to a new line. This will help you keep track of how many trials you have completed. Once you have 10 rows of 5 numbers, you know that you have completed 50 trials. It's also okay to use a die from any board game you may have at home. As you can see on my screen, sometimes when I roll it, I see a question mark that comes up. This stands in for a 1. So it's okay if you don't have a die that matches up exactly, as long as you know which side of the die stands for which number. It's time to continue our 50 trials of the experiment. Now count how many of each number you have in your data. Here I am counting all the ones that I have. When I have my total, I'm going to record it somewhere. Feel free to set up your paper exactly like how mine looks at the bottom. I'm going to use this time to count the rest of my numbers. It's time for step 3, or recording and analyzing our results. Remember, we started with a total of 50 rolls. It is time to answer the question that we first discussed in our hypothesis. What is the probability of the die landing on an even number? In order to calculate this, we're going to count how many rolls of the die landed on an even number. In order to do this, go back to your data and count how many total 2s, 4s, and 6s you had, and then record them on the sheet as well. I had 26 even rolls. We might be missing one more piece of information to calculate this probability. Can you guess what it is? That's right, it's the total number of rolls. Here's our handy probability formula one more time. It's the number of favorable outcomes over the number of total outcomes. In this case, our favorable outcomes are the number of even die rolls, and our total number of outcomes is the total number of die rolls. What's the probability of the die landing on an even number for your dataset? In my experiment, I got 26 out of 50, which is pretty close to 1/2. If we add more trials, we would have gotten even closer to 1/2. So to answer our hypothesis, the probability of the die landing on an even number should be exactly 1/2. One last thing to keep in mind is that your results could have been slightly different than mine, because every time we have trials, they're made of random results. So if you didn't get 26 out of 50, but you got something pretty close, you're on the right track to becoming a great data scientist. In this part of the module, we'll be explaining the probability behind a pack of playing cards, and you'll get to learn some fun magic tricks along the way. Welcome back to Probability Magic. The next step in our module is probability with playing cards. So let's take a look at this deck of cards we have right in front of us. Can you guess how many cards are in a complete deck? Well, the answer is 52. So we're going to take this deck of cards and split it even further. We've got half of our deck with red cards and half of our deck with black cards. And if we had 52 in the whole deck, how many do we have of each color? Well, the answer is 26 red cards and 26 black cards. We can split this even further by taking a look at what kinds of cards we have of each color. We can see that they have different signs on them: spades or clubs, hearts and diamonds. And then within the colors, we've got numbers, 2 to 10, as well as the Jack, Queen, King, and Ace. What if we wanted to know how many 2s do we have in just our black pile? We've got 2 2s out of 26. So the probability of picking out a black 2 from the pile of black cards would be 2 out of 26, or 1 out of 13. Well, what if we wanted to know the probability of picking out a 2 from both of these piles, or picking out a 2 from the entire deck? Well, we've got 1, 2, 3, and 4 total cards with the number 2 on them. And then in our whole deck, we've got 52. So that would be 2 cards out of 52 total cards, which also gives us a probability of 1 out of 13 of picking out a 2 from the entire deck of cards. And now it's time for the probability magic of cards. What I want you to do is focus really hard on a card you want to pick out of this pile. If you're able to focus on it hard enough, maybe I'll be able to read your mind. Alright, let's see if I can do this. Did you pick the Ace of Spades? Let's try this again. So for round 2, think about another card that you would like to pick out of this pile. Okay, is this it? Alrighty, let's try this one more time. Focus on another card. And let's flip it over. Was it a 6 of Spades? If not, that's okay. Turns out it's a little bit harder to make it seem like you're reading minds than you would think. The chances that I would pick out the same card that you were thinking of was only 1 out of 52, or pretty unlikely. So if I didn't pick out a card that you were thinking of, it's because the probability of doing so is actually pretty low. If we perform this trick over and over again, 52 times, I would probably only guess your card one of those times. Okay, now that we've done a lot of hard work, sit back and enjoy this magic trick. I've separated the red cards into hearts and diamonds. And now I'm going to collect them and shuffle them all together. Now that they are well shuffled, I'm going to put down 4 cards in the top row and 5 cards in the bottom row. Here's where it gets interesting. I know that I've shuffled the cards, so I don't know the order that they're in. But I want to guess, do I think I'm going to get a match if I put a card on top? So, nah, I don't think I'm going to get a match for this one. But I think I will for this one. No for this one. Yes for this one. No again. Yes. No. 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 Since the cards are shuffled and I don't know what order they're in, it's probably going to be hard for me to guess correctly. Remember, for all the cards I put face down, I thought they weren't going to match. In this one, I was right, they didn't match. How about this one? Again, not a match. 2 for 2. In the third one, not a match again, we're on a roll. Not a match. Different cards again. And different cards again. That was actually pretty successful. The probability that any 2 cards would match is very low because we had 20 cards to begin with. But so far, we've been right about the cards that didn't match at all. In these last 3 pairs, will I have a Jack of Diamonds, King of Diamonds, and 7 of Diamonds underneath? We'll find out. 1 match. Oh, looks like we got it again. And 2 7s as well. Let's pause the video. So you might be thinking, that seems really unlikely we'd be getting so many matches. If this was actually a bunch of random events, it would have been very difficult to get a match. We were only able to get them because of a magic trick that involves some sneaky shuffling of the cards. We learned a lot during this module. Take a look at all of the concepts we covered. So great job and congratulations on all of your hard work. Thank you so much for joining Probability Magic.